Ladies and gentlemen, once again, we are delighted to come to the third day of the workshop, the AMMnet workshop, in collaboration with IMECI here at the prestigious University of Campinas, State University of Campinas, and in collaboration also with SALI at UFBA. So we want to have some presentations from what the students have learned from this workshop. So we have about 4 or 5 groups of great students here today. And the first person that will be opening the floor for us to show us some of his results and the experiments he has done with the machine learning on malaria data is Group 1, that is Negli. Please give him welcome, Negli.
Thank you very much. Okay, so good afternoon, and well, this is the presentation of our group's work, which is composed by myself, Negli Gallardo, and Shirley Metelus. And our task was to train 10 models with the malaria data, and we were assigned to do it balancing the data with random oversampling. So I am going to show you here more or less what we did. Maybe just to let you know that this is our first interaction with machine learning. So we are not expert with Shirley, but we did our best to try to train the models and to plot the results. So this was how the data was at the beginning in balance. You can see that we have less frequency in the severe cases from malaria diagnosis, right? So then we perform an overfitting, oversampling, random oversampling to balance the data. And this is the result that we got. You see that they are more close than in the original data. And what we did to perform the oversampling was we run with the function overslope, I guess is the name, from the ROSE package. So we created new data sets with 75% of the data for training and 25% for the data to testing. And then we run the 10 models, and here we have some of the results. This was for the CVM model, and as you can see here, we plot how it performed. The green, we were just talking about, and we were supposing that when it is green is because the prediction, the accuracy of the prediction was correct, but for example, this is 20 that missed, right? 21 that missed, and 13 and 45 that was performed correctly. And then we saw that in this first training model, the variable that has more importance was Coca-Cola urine. I guess is that the urine is dark. It's I suppose. Then we perform the random forest. We obtained these results, and in this case age was the most important predictor, and so forth. Here we have LR, LR again urine, and we did all the 10 training models, KNN.
Sorry, a question.
Yes.
That importance that you have several variables.
Yes.
So you can use these to cut, for example, to use only the first 10, or how you use this information?
In this case, we just have all these variables in the dataset, And I am guessing that the model is fitting it with all the variables that we are providing, like these are potential predictors.
Okay.
I guess when we saw the results and we can construct a better model, because for example, fever cold is very low. So maybe we can, if we run a new model, we can eliminate those variables with less than, let's say, 40% of importance in the model. I am supposing, because I have not worked with this type of analysis. So it's not an educated guess, it's the opposite of an educated guess, in my case. And sorry, because I could not erase this results that was part of the analysis, but here is the other one. And we can see here that again age, we saw that age or the color of dark color in urine are like the variables that were more important in each of the models that we fit. And then we will get to the final result, and we can compare how the models performed, and based on the accuracy we can have like a general idea of which of the models maybe perform better. In our case, for example, random forest, which is in this line, has a mean of 84%. I think that because we are not, we have not been working with this type of methodology, we don't know if there is another metric that we should take into account to decide which of the models could perform better. But based on what we were hearing during these 3 days, and the mean of the accuracy of the models was one of the metrics that was mentioned, we are guessing that maybe random forest in our case was the best model for this data. And then we plot these metrics, and we can see that here is the random forest is 84%. And other thing that maybe is important in these cases is that the confidence intervals are closer in this model than, for example, in this one or in this one. So I am guessing that you are going to use this information to decide which of the models you should use for your data. So more or less that's why we were able to perform. So thank you very much for your attention.
So it's not a guess, you are correct.
Oh, thank you. Good. We're paying attention well.
What is the meaning of kappa?
Kappa is also a matrix
Measure?
that measures the closeness of the predicted and the actual.
Ah, okay,
Yes,
nice.
yes, it's from
Oh.
-1 to 1. Okay, so yes.
So again, the random forest is better.
It's better.
Yes.
So you did before balancing and after balancing?
No, we just did. Well, we run the original code that you that you gave to us, and we saw the results, and then we balanced the data, and we run the balanced data, and we just presented the balanced data.
Oh.
We were trying to compare it and bring it to you, but we didn't have enough time to put it on the presentation.
You tried.
Yeah.
So which one is better, after balancing or before balancing?
After balance.
After balancing is better.
Yes,
Great.
yes, perform very well. For example, in the case of random forest, before balancing, it was like 64% in accuracy, and here is 84%.
84. There are other accuracy measures. Can you go up to your confusion matrix results? Did you? Yes, up. This one. These are the measures. you use only accuracy. This is what we said.
Obviously, yeah.
Sensitivity is there, specificity, recall, F1, sensitivity and recall is the same. You can see it's the same number.
Yeah.
So it's the same. And P, V, and precision is also the same.
Yes.
The
Yes.
same. So F1 score is the harmonic mean of precision and recall. So it's also useful. This is maybe before balancing, it's quite low. So the balance accuracy is also useful for metrics, not only accuracy. So you can use sensitivity, you can use specificity, you can use balance accuracy.
Okay.
The higher the better for balance accuracy.
Okay.
Yes, especially for imbalanced data sets.
Balance it. We can see the result of the random forest. Maybe it has better numbers.
Yeah.
Let me see.
Yeah, so kappa is there. Then use area under the ROC curve. Did you do that?
No.
No. Okay.
That sounds something more complicated.
Yeah. Then this is showing us that this importance, this importance, variable importance, is showing us that go to the variable importance. You can see the upper parameter tuning there.
Here.
It's done it automatically. This one, the variable importance. This one, yes. It shows that age is a major contributor, major predictor.
Okay, okay.
As far as this model is concerned. Okay.
It changed with other type of model, right?
Yes. With
Has
the
other variables, other predictors
yeah.
that are more important.
So the one that you believe more is the one
Based on age.
below is the one that is the model that is the best.
The best.
So you believe the
Yes.
variable
The random.
importance of the
Is
best
age.
model.
Okay. Okay.
Yes.
Okay.
And is this for random forest?
Yes.
This is for random forest.
Yes.
Then this age.
This is
Okay.
random
That
forest.
explains much variation in the diagnosis of the patients.
Okay.
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 So please keep it up. See how you can
Yes.
develop this.
Yes, sure,
More.
sure. We like it very much.
Yeah.
As I told you, that's the first exposure to this type of methodology, but I like it very much.
You like
And
it?
yeah, it's very nice to learn by doing, right?
Okay.
Is the way I think it's the best way to learn, because you are going to learn for your mistakes and for the things that you do right. So I like it very much. Thank you very much.
Thank you, Negli. Next group, quickly. Yes. Next group.
Group 2 is right.
Thank you. Put there. And AMMnet.
Oh, there's a USB cable up there. Here, cable.
Are we going to present now? And just put it okay, sure.
Good afternoon, ladies and gentlemen. I want to use this opportunity to thank the organization of this, the organizers of this conference. Is quite an inspiring one. It's really interesting. I know there's being something that you are seeing for the first time, there's a lot of challenges, but I believe that with time, it's going to yield a very wonderful harvest. So we're here to just give a summary of our own work myself, Priscilla, and Christiane. So we're just going to give a summary because most of the things that we would have talked about, it has been said by the other group, so it's more or less the same. So we were given the unbalanced data, and we were asked to use ADSYM to balance our own. So this is the unbalanced data, and you can see that the percentage, they are just varied between non-severe and severe. You can see that they are not just balanced. So we've already been told that if you work with this kind of data, you may be overestimating, or you may be getting your false positive, false negative. So to make sure that you get a precise result that can stand the test of time, you need to do a preliminary analysis, which is balancing of the data. So we are giving the group to balance using the ADSYM. Yes. Yes. So we were able to do it. This is a comparison of all the models with the balanced data. So we tried to compare all the models with the balanced data by fitting using 75% of the test.
Yes, 70 and 30.
75, 25. 70, yeah, okay. So if you look at the slides, you can see that it is the boosting and the SVM that is more or less giving us a good fit. If you look at these two, because number one, there is less variation. There is less variation compared with random forest or LVQ or KNN. Or so you will be looking at these models between boosting, SVM, NN, and this model. So, and if you look at the kappa, you can see that this kappa is more or less. But I think Professor Awe should be able to help us to use kappa to know how to be able to identify the best fit, because I'm not sure I got the interpretation of kappa, using kappa to be able to identify the best model that you should use. So, but based on what we're able to do, we're able to, summarize the analysis and then try to find out the best fit of the model.
Priscilla, do you know why those three models can catch better the behavior of the data? Do you want an interpretation of? Sorry, the question. I am theoretical statistician.
That's why. Why was your question?
My question is, why those specific models, the third, fourth, and the last one, these three that you mentioned, I don't remember the name of MB, are the best models, or are the models that can catch the behavior of the data in a better way? Why this happens? What do you think about in your interpretation? Naive.
Well, I just feel that probably the model were able to capture the main predictors. It was able to bring out, to summarize the main predictors, and there may not be many outliers in this model. To my own, that's what I think. Because sometimes when there are too many outliers, it could shift the mean. It could make the mean so, the mean will be trying to be at the center to centralize everything, but one will be pulling it. So I think outliers could be one of the factors. And then when we have too many missing variables, but I'm not sure this data has missing data. So I'm not sure, I don't know. Professor Awe may talk about that. So that's what I think. This particular technique, I'm just new to it. We are just babies and we are just trying to, see what we can do to help ourselves and improve ourselves in this technique. So,
Thank you.
Yes,
Finish.
This is actually the first part of the presentation because we here put the unbalanced data with these curves, also rock curves. And we have another file with the balanced data for trying to see the difference. So this is the first approach, just for showing to you that this is not a correct approach. And the second file, we try to put that in a very brief way, without putting too much details about that. So here's the balanced data, as Priscilla told you. At the beginning was in those two numbers, and with this plot also that Priscilla showed you. And we use this method that we actually we don't know the details about the method, but I think in summary put the data in a balanced way. So I think it's something useful. And after we apply this method, the proportion changed a lot. So after that, we apply actually the 10 models that we ran. This is the bar plot showing that, the severe, and not severe, or severe at the right and the left, not severe. And after we put this, we try to put all of the information in just one plot. We could present to you the confusion matrix, but we didn't consider that was important at this moment. So we just put this plot, and as Priscilla said, well, in this case, I think the result was similar, but of course are better. I think the boosting random forest and support vector machine. In the course, we learned something about random forest and decision tree, and also some comments about bagging and boosting, but I don't remember the details about that. Sorry. And here we have the other measure for trying to compare the models, and we think that these three models are the best. If we saw, for example, we see the median value, that is the black point, and here also I think is very similar. So these two measures I think show us that these three models are the best. But we don't know why are the best. So maybe we could study in more details after the course the theory, because in this moment we really don't know why one model is the best. I'm not sure. I think that in this area, in my opinion, I think probably there's no theoretical reason for a model to be better to another. So that's my impression. But of course, it's just an impression, could be wrong. And after we present this...
Let me make a comment. The first group, what was the best model in the first group?
Random forest.
Random forest.
Yes.
Negli, what was the best model for you?
Random forest.
Random forest. Okay, which was your method?
Oversampling.
Oversampling. Second group?
Yeah, the second.
Yeah, the second, I'm sorry, yeah. This one now, boosting. Now, you can see those models are performing well because they are assemble models. That's what I mentioned in class. Assemble, you remember when I was explaining?
Yes.
Or when Tatiana was explaining, or someone else.
But in this random forest assemble, kind of the decision tree.
Boosting and random forest, they are assemble models.
Yes.
So combination of predictions from individual models to make it better.
Yeah, I don't know, but I think in this you just have one model, and this you compare different kind of models, a kind of mixture of models.
Mixture of models.
Okay.
Even random forest is also a mixture of models.
Okay.
Mixture of decision trees.
Okay.
Okay, so do you have the answer now?
Okay.
Is your doubt cleared now? So that is why most of the time, that's why I was asking for the first group, assemble model will do better. Also here, boosting will do better, right? So they are more complex than these individual models, like naive Bayes, KNN. Neural network is also great, it's a deep learning model, but Ensemble is performing better in this case. So that shows, you can see bagging is also close to the top.
Yes.
Right. But SVM is there because it's also very powerful for any type of binary classification. So that could be the reason. So we're waiting for other groups. We're going to see what is the best model for them as well. So I will have been surprised if maybe logistic regression or KNN is better than boosting, you know. You get what I'm saying? So that is just a simple explanation. But in details, the theoretical details, the mathematical explanations of the models, of the each of the models, we can also do that, but maybe there's no time for it. But the simple explanation is that it's a combination of several models. Is that okay?
Yes, yes, yeah, it's okay. And I think it's important that probably these models in almost of the cases, but not always, are the best models, I think.
Yes.
And actually in the logistic regression, I think you said something about regularization when you have a lot of predictor variables.
No, not for logistic regression. There's a variant of logistic regression. There's a lasso logistic regression or reach.
Yes, but is it a logistic regression with lasso or logistic regression plus
with
reach?
Yeah, or
And we use this
elasticness.
regularization method.
Yeah.
When
Where?
you finish our
Continue.
it's a question.
Oh, question.
We're able to fit the AUC, but we don't know the interpretation. That's what I wanted to say. We don't know the interpretation. We don't know how to really, use it to be able to identify, we just don't, we couldn't do that.
Okay. So, so this, the higher the better. This is area under the curve. The interpretation is so simple. True positive rate. Look at true positive rate. You saw it there. The rate at which the model is predicting the positive, the true positive, versus the rate at which it is predicting false positive. So that's the plot of the AUC. Are you getting it?
Very well.
So the higher, the better. The higher this area, the better. That's the interpretation. So don't say you don't know the interpretation. That's the interpretation. That's what we said. So you just need to build confidence. And that is what we are doing in this workshop. We build your confidence.
Exactly.
Yeah, to build your
And
confidence.
I think this kind of workshop should be done serious. It's not a. It's,
Thank you.
You can't use 3 days to this.
Yes.
It needs to be a comprehensive program. Something that can come out maybe once in 3 months.
Yes.
Gather students, because it's just like learning how to drive a car. If you drop it, you won't be able to ride it. So I'm just using the opportunity to ask the organizers to please do more. We need more. We need to,
Thank you. So we are applying for more sponsorship.
Yes,
So
please.
do more for you guys, okay?
Please.
Okay. Thank you. So show me the other one. I saw 73 somewhere. The other graph is good, right? This one is higher. I saw 73. Yeah, this one. You see, this is a good one. Is there anything above 70 is still is good. Yes, and that's random.
The random forest.
So that's clarifying your doubts more. If the AUC is also high, the sensitivity is high, the balance accuracy is high, or the accuracy is high. Maybe after balancing, you do the accuracy and it's high, and this one is also high, then you can suggest random forest to the clinic, maybe this malaria clinic. They can now deploy it in their, automate it in their system. So what we are doing, this is artificial intelligence. Artificial intelligence is a field that tries to, make machines or computers to mimic humans, right? And even make machines to do better than humans, do what humans can do, and even do it better. That's why it's an evolving field, So that is the essence of artificial intelligence here. Such that if you have built a model now, And if you work more on it, you tune it better, probably this AUC will be higher. Maybe get it up to 80 something or 90 something or 95. Not perfectly 100. Anything 100 is not also good in real life, right? There must be a little form of variation in life, right? So if you can get it to a better level, and then you compare with all comparisons you can, and then you can deploy this to the clinic, and then they put it in their system, and then the patients will come to a table. Doesn't have to go and see the doctor. Will come to a table. What's those symptoms you saw there? Do you have Coca-Cola in it? Yes, put it there. Do you have this? Put it there. It brings out results. You have severe malaria. That's what the usefulness of this thing. So that's the interpretation.
Okay, that is very nice to say. But
So from another perspective,
yes, from another perspective, we try to say, because machines, like the professor talked about yesterday, that sometimes because the X-ray was reading the name on the X-ray, that it gave like 100%. So because of that error, we try to balance it also with the physician's decision. So we do not say AI should replace.
Who should replace?
Be like a support.
Yes, a support. That's another balanced perspective. So but in
I'm very quick.
yeah,
It's quite quick.
but that's where we are going. This is a very good debate.
Yeah.
That's where we are going. So what you are saying now, in banks, they are already using AI. There are robots paying at the gate of the bank, right? So what you are saying is that after the robot has paid, you should go there again and collect the money and repay.
Because it's life and death. You know, life and
But-
death. If you take money or not, you will die.
You
So
get it.
No,
life
but
and
since
You get what I'm
it's, but
saying?
since it's predictive.
The banks, ATM is artificial, is a kind of
Yes.
artificial intelligence, the vending machine.
Yes.
How do you know that, you see, a program has been written inside that ATM. It doesn't happen by chance. This type of programs have been written for the ATM, for the money vending machine to run, to count the money. Yeah. So if you are saying that, I appreciate the medical view because it's life and death. But if you are saying that, does it mean that even in the bank, that they will now
on repeating the
demand?
process.
No, you can't
You
keep
can't
on
do that.
reinventing the wheel.
You can't.
You understand?
Medicine.
But she's still a doctor arguing that.
Otherwise, why would they have used AI?
Because there can be error.
But I
Yeah.
think that the question that here is that you have some subjective elements
Yes.
about the knowledge
Yeah.
that need to be incorporated in the analysis.
Yeah.
Because you can develop some specific code to process the information, but you have some kind of information that is
Yes.
of subjective nature,
Yeah.
and this needs to be incorporated.
Yeah.
And sometimes appear that you are trying to remove this from the process, especially in medical science, because of course the experience of the person, of the doctor, needs to be incorporated in the process. So this is the hard part. That this is not a machine here that can do for us.
Sorry, another thing is because there are other diseases, like 1,000 diseases that can cause Coca-Cola use.
Okay.
Exactly.
Yeah,
So
yeah.
you can't just say, if you have this symptom and this symptom, you have this. It has to be in support. Maybe we can bring a test of COVID is positive or malaria is positive.
But I want to say that that's where we are going. That's where we are going. Where machine will be able to replace.
Narrow
Yes,
the
narrow
doctor's
the error.
field, because doctor is
Exactly.
faced with so many
Yeah.
options.
Exactly.
But with machine, this thing you've narrowed where you'll be looking at.
Exactly.
In fact, what it helps now,
Yeah.
how do we see it in
That's the
medicine? What
future.
we do is this. A doctor is not clear, but the machine is clear. You choose what the machine says.
Exactly.
But when the doctor is says yes, and the machine
Exactly.
says no, you choose what the doctor says.
For now.
Yes.
That's why we may not choose. That's why we go and check the accuracy of this model that was deployed more. You know, it continues.
Yes.
when it's saying wrongly, I mean, it's predicting wrongly in real life. Sometimes they remove it, they bring it down, and reload. That's why they keep on hiring data scientists. That's the job of data science. If not, one model will serve for long. No, they continue working on it, it's an iterative process based on data that is being collected. So the machine learners will sit behind the scene and keep running this model to deploy.
It's really helping nowadays because, for example, we developed the risk calculators for PPH, and it helps to make very quick decisions, and it saves lives.
Yeah.
So I do not want to underestimate the role of AI.
Yes.
Like,
So
we should not
AI,
replace
they
what
are
we use
still,
together.
it's still a big argument, but that is, you have to join the winning team. Yes, that's where we are going. Where AI, that's why we are organizing this workshop, to enlighten people. Yes, time.
It saves money,
Yes.
it saves even personnel.
It saves
Something,
time.
you know, when in a hospital,
Money.
there is no one person doing an analysis. There may be 4 or 5 people. This person is looking at this person is looking at this. But if you use this AI, it narrows the factors the doctor will start with. And he can start from there. So assuming that he doesn't get what he's looking for, then he can now explore other options. But this narrows the disease progression or the disease that you are looking at in a patient.
So please, let's understand the interpretation. You understand the interpretation now, the usefulness of what you have done.
It's making big sense now.
It's making sense now.
Very well.
So this is also part of the lecture, part of the workshop. That's why we wanted you to present, so that you can have opportunity to feel it firsthand, and then we can explain.
Thank you.
So, and this can be done for any disease, any infectious disease. So that's the usefulness.
Thank you so much.
Welcome.
I was late to one debate.
Please sit. Please. Okay. Welcome. Please. Ademir?
Eu acho que me parece que é melhor você. Você não tem pendrive? Você tem um e-mail? Manda para o e-mail. E aí você abre aqui. Não sei se compõe na abre, eu vou abrir meu e-mail para puxar o dela. Eu acho que meu e-mail já estava aberto, né? De hoje de manhã.
O Gmail abre
Que eu
anônimo. O Gmail abre anônimo, mas não fica assim.
Ah, tá bom. Se algum grupo precisar enviar para o meu e-mail, pode mandar que eu abro. If anyone needs to send by email, they can open. Okay, I think it's in the computer prof. It's in the computer. Yeah, our presentation. No, she sent. Okay. I think. Sorry for that. My life is what it is.
Please don't forget to put down your name for certificate. You have with Douglas.
That's
Yeah, the paper was.
The artificial intelligence is wrong.
It's interesting, right?
Honestly.
Too much data.
You guys try because it's not a 3 days. It's not something that we try
They
to.
were explaining some concepts that you learn in one semester.
Yes.
Explain in 1 hour,
Exactly.
so it's...
Exactly. She said it. She said that most of these things people learn it under 3 months. You know, so it's more like a crash program.
Deixa eu see. Melhor, né?
Yes, this one. So what are the members? Is this your list? Sorry.
This is the presentation from the group 2, which is comprised by me and by Mike and I. First of all, I would like to thank everyone who was involved in the organization of this workshop, especially Professora Veronica, who invited us. Our group was assigned to do undersampling, and I will show how it affected the data. So you can see how it was before, and we try to alleviate the class overlap by doing so and balance the data set. Now I will show some of the effects of this comparing the matrix of the models. I will not go deep in every one because the results are very general. So I will just point out some differences and the results in general. We have one for SVM. We can see, for example, that diarrhea and headache are the most important for the diagnosis, which is, this is the undersample version. We have random forest here, and in which age is the more important. What I want to point out about those is that when you undersample something, we can tell that the sensitivity goes down. So the proportion of actual positives correctly identified by the model goes down, and the specificity, the proportion of actual negatives correctly identified by the model increase. Also, the precision, which is the proportion of true positives among the instances identified as positive, also decreases. However, the F1 score, which is a measure that combines precision and recall, goes up, which is really useful when you need a balance between precision and recall. You can tell this is happening in every one of the matrices. Here we have a RRC curve, in this case especially of K and N, in which we have the relation between false and true positive rates, and you have AUC, which is the rate that measures the ability of the model of distinguishing between classes. So So the ability of it distinguishing between a true positive and a false positive and classifying it as what it actually is. And it has a rate of 0.53, and when it is closer to 1, it means it is more precise. We have the same rates I talked about: sensitivity, specificity, and F1 score for all of this. I just wanted to show all I have done for other models. And here we have a comparison of the models when it comes to accuracy and kappa. Accuracy means the overall correctness of the model. So the proportion correctly classified by it, and you can tell in this one is it is done better by SVM and NB and boosting, which can be, in my opinion, because of how these models can work with complex relationship between variables and a number of various data classes and high dimensional spaces. And it also is true for kappa, which is a measure of agreement between two variables and interrate reliability. So that's the presentation.
Hola, Maria, I have a question.
Yes.
It's a very fast question.
Yes.
When you have a complex model that offers a good index of sensitivity or kappa and maybe you are increasing also the possibility of overfitting or not? How to control the overfit, the possible overfitting? So this is
That's a good question. Well, having a complex model does not mean that it will bring about overfitting.
no.
Yeah. Is that what you are saying?
I think that I am thinking in a model with a lot of parameters that in general they will fit very well in a
Yes.
specific kind of
Yes.
data.
But in
You have the
some of these complex ones, that's usually their disadvantage. Like XGBoost,
Okay.
like even random forest,
Okay.
you are correct.
You need to be aware.
You are
about-
correct.
okay.
Yes, you are correct. But then that is why you need to tune, you need to prune the trees sometimes. You prune the
Okay,
trees,
okay.
you tune it, and all those things I was talking about in the morning,
Yeah.
especially for this type of models.
So you need to take into consideration this step
Yes.
in order to control the overfitting.
To control the overfitting, yes, because most of these type of models suffer from overfitting.
That is,
Yes,
they are
those,
so fitted to the data that the ability to predict something outside decrease. But if you have some elements,
measures, yes, to control that. Because if you read the theory, one of the disadvantages of these big models is overfitting. But generally, it doesn't mean, except for these tree-based models. But other models that are complex doesn't mean they will naturally overfit. But one of the major disadvantages of the tree-based models, the advanced tree-based models, the XGBoost, the random forest, and all of these other types, there is overfitting. Right. Okay. Your question.
I was looking at, most of the groups that presented. I
Yes.
saw that H
Yes,
is
age.
constantly having more effects
More effect.
in almost all the
the
models.
models.
So, and I know that if it is in statistics,
Yeah.
we do something like checking for multicollinearity between the predictor to see whether there's, so, yes, looking at if two independent variables, yes, are correlated and maybe influencing the response. So I don't know if there's a package here that does something like that, that takes that into consideration, you know, and what they normally do is to centralize the continuous variable. And you know, you are looking at, most of the predictors are categorical. I think it's only age that is
yes, that's why I said you should pre-process. I said it yesterday, so that one scale will not
give more weight to the other one than
exactly.
especially.
But yes, but at the same time, because this question you are asking right now got me thinking last night.
Yeah.
But I tried to also look at the fact that looking at the predictors, we are actually looking at what could, because we are talking about malaria, right? So I was also thinking about it last night, that could it be that age actually has a very significant like importance when it comes to maybe severity of malaria on a patient?
Yes, I was coming to that. It is.
Yes, so I was thinking maybe that is why, you know, it kept showing on.
Yes, that is why, because it is the most varied among all the variables. If you look at the other variables, you see just categorical 1 0 1 0 1 0. You get it. But age now is a general clinic.
Yeah.
Age from 3 to 70 something.
Is varying.
Is varying so much.
Variation, which could
Yeah.
be influencing,
That's
giving more power to
exactly.
predict the response.
Exactly. So if it depends on what your objective, depends on what you are working on. If age is of importance to your
Or is there
organization,
a way we can tell the model not to concentrate much on age?
yes,
We can also
a
remove
lot.
age
We
and
can
then look
remove-
at how the model varies. It's more like a
That
trial
is
and
it.
error. We can remove
Exactly.
age and then watch out to see whether there is one that is
Yeah.
now showing a better fit, or whether all of them
If
are on the
there's
same
time.
scale.
Exactly.
So
So that could be a future research question. And I told you that we may want to work on this data further. Already I have 2 researchers there. I want to work on with it with me. So we will remove age, we will put it back, we will watch it, a lot of things, and you can even take the log of age. You can do a lot
Exactly.
of things.
Or even,
Right.
or you can also categorize age and make it an ordinary
can also-
variable, so that
thank
all of them
you.
can be
Exactly.
class variables. So we are now
Exactly.
using class to predict class.
Exactly. So all these things are possible, right? So please, the major thing or the most important thing is for you to have the idea. That is what we have given you. So you can fly from here. You can try different things, right? So thank you for your presentation. You want to say more?
I want to take a picture with our slides.
You are being recorded.
Yes. You are very
Oh,
good.
sorry.
Just say 1 or 2 things. Okay. So this is a slide. Okay.
Okay. Mike.
One more, please.
Oh, one more. Okay.
Yes. Cheers.
Thank you.
Thank you so much.
Last group.
The future professors.
Você precisa de ajuda? Não. Tá bom?
Eles se viram.
Não? Eles se viram?
Eles são espertos, se viram.
É. São meus alunos. São super.
Good afternoon, everyone. Today we are presenting a work that we did in this workshop in which we use 12 modeling machine learning supervised classification models to predict whether the person has severe malaria or not severe malaria based in predictions like age and other things. I'm Anderson. I'm an undergrad student here in Unicamp studying, I'm doing bachelor's in statistics, and this is
And I'm Nicholas. I'm first year on bachelor statistics, second period this year, so I'm pretty new and stuff.
I'm the fourth semester. Okay, let's start it. Here, the proposition of our group was handling data imbalance with smooch. What is smooch? Smooch is synthetic minority oversampling technique. We will see in the presentation the consequence of using balanced data and balanced data to work with prediction with machine learning. To summarize, Smooch, they create data based in iterations in which you take a data and you make a vector to the k nearest data to it. And the new data fabricated, the artificial data, will be in the half of this vector. And here we can see in the first plot the raw data. There is the imbalanced data, and it is clear that we have there the not severe and the severe, and then after the balanced data by Smooch. Okay. The first model that we used was the SVM, that is support vector machines, and we did it with imbalanced data. Here we already can see a lot of metrics. The first one there is a matrix, the confusion matrix, and the interpretation is that 55 is the true negatives, the 25 is the false negatives, the 0 under the 55 is the false positive, and the other 0 is the true negative. Here we already can see that is a very bad model, because usually when we have 0 sensitivity or 1 sensitivity, 0 specificity or 1 specificity, that shows that we have a bad model, because sensitivity is the rate of true positives and the specificity is the rate of true negatives. And as we can see, he couldn't predict any true positive, but he could predict all true negative, and that means nothing in predicting. Here we can see other metrics. We use accuracy, we have the F1 score, precision, the kappa. In our work to compare one model to another, we will be using the metrics kappa and accuracy. Accuracy is pretty much self-explanatory. Kappa, on the other hand, is a metric that goes from -1 to 1. So the higher the kappa, the better is the model. Here we have 0 as kappa. And accuracy is a number between 0 and 1, and the higher the better also. After plotting this, we could see the importance plot in the right. And here we see which one was the best predictor to predict this data. But here we are using imbalanced data, and we got a bad model. so doesn't matter much the importance here. Going next, we use the same model, but this time we use balanced data. We can already see the confusion matrix is not with zeros and in any of the cells. So we have a sensitivity of 0.5128 and specificity of 0.6. So this is a much better model with balanced data than the imbalanced data. Because of this, we can predict also the true positives and true negatives. Here we have a kappa of 0.2 that is already higher than 0, showing that is a better model. The accuracy was lower, but in the previous, it is not a good metric to measure that. We need to use another ones. Because in the previous, we are not predicting nothing. We were saying everything was negative. That's why we predict all the true negatives. And here we got a... The plot importance here shown us that prostraction was the primary predictor to predict the data to know if they were either severe malaria or not severe malaria. And I forgot to say, but we are doing all this machine learning testing with cross-validation. The cross-validation uses 10 folds and 5 repetitions. Okay. Here we go to another model, random forest model, and we also see the imbalanced data. And we can already see the confusion matrix that we have a 0. That means we have a 0 in the true negatives. And that shows that is a very bad model using balanced data. And this is shown during the sensitivity. Actually, it was a true positive. Is that the matrix is reversed for some reason. In this model, we could do the ROC curve of the random forest. In the other ones, we couldn't. And the interpretation here is that we have the relationship between true positive rate and false positive rate. So the objective here is to predict the true positive rate. So we need to get the high, and the false positive rate, we need to get the lower. And the AUC is the area under curve. AUC would be the probability of getting a true positive rate prediction rather than a false positive rate prediction. Here we got in the importance the plot that the age was the most important. But as we saw, this is a very bad model because of the confusion matrix. In the other hand, in the balanced data, we can see the confusion matrix is spread. So the sensitivity goes to 0.4 and the specificity goes to 0.5. Here we have a couple of 0.1, while in the other one, we have a minus 0.04. So it already shows that this model using balanced data will be a better model than the imbalanced data using random forest. And this will go to most of the models. In the majority of them, the balanced data shows better results than the imbalanced data. We can see all the other metrics. And here in the importance, in the other hand, the prostraction again got the most important predictor. And here we have a AUC of 0.63. while in the other one we had a 0.53, showing that this is indeed a better model. And we did this for the key and nearest neighbors, for the logistic regression, and we can see here we have a low sensitivity, a high specificity, and then we have a more spread confusion matrix with the balanced data, showing that it is a better model with balanced data. The kappa goes from 0.03 to minus 0.06, so the kappa got lower, and the accuracy too. So this will be one of the exceptions, because here we got better metrics at imbalanced data, and this is rare. This is rare. Also the AUC, that is another metric, got lower with balanced data. So here we see that logistic regression is one of the exceptions. Here, again, he chose prostraction as the most important predictor. The bagging model. The bagging model with imbalanced data, we got these metrics and the most important predictor age. While going to the balanced data, we got this one. And there is a slight better kappa and a worse accuracy. So this also is showing that bagging is better with not balancing data. I'm not showing the right examples here. Now we go to neural net. The neural net imbalanced data shown us these metrics. We get 0.1 kappa and 0.5 accuracy. And here we got 0.5 accuracy and 0.005 kappa. So we don't have in the both of them the ROC curve to decide which one is better. But in the end of it all, we will compare them into a box plot graph and see which one in fact is better. Now I will pass to Nicholas.
What is the goal of the Magnier test? What is is comparing what?
What?
The Magnier test.
Oh, McNamar.
The combined one, right?
The combined,
No,
is
no, not the
comparing
combined one.
the cross-validation results.
The cross-validation.
Results.
It's a test for cross-validation.
Yes.
Some of them show results nearly to 1
McNamar
as
says
the,
can also be
the
reported.
bagging model, and some of them as this. If Bayes shows something like really, really small, like under an exponential of -6. So, yeah, the next one was Navy Bayes. That was kind of like our worst model in imbalanced data, because it showed 55 not severe, like true negatives, but in fact like 25 severe cases in model, but it predicts as not severe, so it means false negative. It showed a kappa of 0 and accuracy of 68%. But in F1 score and positive red value, it shows nothing, even a recall and sensitivity of 0, but a specificity of 1, and of course this is that, yeah, that's it, and a specificity of 1. So we show all the true negatives.
The sensitivity is the true positive and the specificity.
True negatives. Yeah, so it shows all the true negatives of our sample, of this randomic sample that we set C, but it didn't show any true positive of the sample. So it's probably Yeah, that's the most important stuff. But then here we have more dispersion, and of course a p-value that's more close. It's it's more than 0, and of course I have one score higher than the other. Sensitivity that exists, it's 0.5, and show that it was a good prediction with some of the importance. Some of the importance stay in the same position, like prostraction. It was the same important for imbalanced and balanced data, just having a low difference between one and another. Then we have linear discrimination analysis. We did with the imbalanced, show 50 of true negatives and just 3 from true positives with a huge value of specificity, but accuracy of 66% with prostraction and diarrhea was the top 2 most important. Then when you change for the balance, it kind of dispersed more. So it shown 25 of true negative and 15 of true positive with lower kappa, but with a p-value near to 1. So, and with area under curve of 0.2, with prostraction in the most important, followed by fatigue. We have linear vector quantization. So, most of the models that we use show kind of well the predictions of true negative, but when it comes for the positives, even the prediction or the true positive, it goes really, really bad. Like 3 of true positives, really low for sample. An accuracy of 58%, and a couple negative 0.9. And with, of course, the p-value 0.08. Then, of course, the importance with prostraction, diarrhea, and headache. And then, after change to balance, the data seem more linear, with spreading better between not severe and severe, with a kappa really higher, and the precision better, more accuracy than the imbalanced data. Even sensitivity, specificity, or the F1 score was higher with balanced data than imbalanced data. Then, boosting model, combining all, we got this extreme situation that got all the true negatives, but didn't get any net positives right. So it got 25 false negative, with an accuracy of 68%. P-value really, really bad, like exponential of -6. And then F1 score of unknown, precision unknown, or recall equals 0. Then when we switch up for the boosting model, we have like 0.66 in as AUC, and then the p-value was the higher, I guess, in our sample during the models was equals to 1. The kappa was 0.05, 0.04, and well, that's some of the most spread data between non-severe and severe situation, even reference or prediction. Then we did the decision tree model to analyze how they were showing up some results we like to analyze. And it's the same stuff, similar to the boosting model without balanced data, with imbalanced data. It shows similar p-value, the same reference and prediction values, and I guess the same recurrence. Yeah, and the same recurrence to this model. And then here we have 0.61 of curve of decision tree. And one interesting fact is this graph of importance. In decision tree model, it was null. It wasn't able to plot the graph. It was empty. In this case here, it shows only it considered importance just 5 variables of the 15 that we have in the sample. And then adaptive boosting, we did this analysis because when we did the boosting model and the code programmation, it pre-processing the data, and it showing a value of AUC, mostly the AUC, as 0.66. But when we did the adaptive boosting, here, that's the most interesting situation. Without the pre-processing, it got like less 0.06% of error. So it shows that for adaptive boosting for ADA, it's better you compile the data before continue evaluation. And then we compare all the data that we had, continuing minimum, maximum, median, and mean, with the kappa and accuracy of the data. And we plot this box plot to show the K and N. It showed the best result of accuracy with the last range between the minimum value and the maximum value, and even with the highest mean, and kappa either.
As we saw in this presentation, most of the models got the prostraction as the most important predictor. Most of them, as we saw. And here we just compared the balanced data results since they were better. We didn't include the imbalanced data. And here we can't see clearly which one is the best, but here in the box plot graph, we can see that KNN is the best model that we got.
For which one?
For balance.
After balance.
Yes, after balancing data.
Which type of balancing?
Smooth.
Smooth?
Yes.
Interesting.
So this is it. Someone has any questions?
Okay, question.
And did you try to find out why the model with unbalanced data fitted well for the logistic regression than the unbalanced? Well, could it be what we are talking about earlier on, that overfitting of categorical models? Could it be the explanation? So if you can't, I'm just throwing it open to everybody here. So,
It's an answer. So the answer is yes. The answer is yes. Yes, you need to do more work. So we have to sit down and improve this work until it's very good that we can even publish.
During our work, most of all the samples we did had seeds to randomize stuff to be less, robotic or chose the best samples always. We find a really good situation during our exploratory data was if one specific seed, the difference between the data of severity and non-severity data, it was kind of minimal. It was like 2 of difference between one another. And
you have a very wonderful result with your balanced data. You know, we are trying to ensure that we get the best fit that, you know, that could really not be exposed to any criticism, you know. So if the aim of the work is for us to make sure that we use the best data possible.
Yes.
And now we are using unbalanced data and we're getting a better result for the logistic model than the balanced data. So
Yes.
we just want us to have it in mind.
Okay, that could happen, but as we saw, was the minority of the case. Yeah, that could happen. It's random.
He has already answered this.
we even try like 1,000 times running the same model to see if it happens in difference.
He already answered it. Thank you so much.
Thank you. Next one. So, So we're getting close to the end. We want to tell you about the inauguration of AMMnet in Brazil. If you are interested in joining AMMnet, it's a professional body which you can join, and we have a lot of activities that can really help you in your career. So please feel free to check out the website of AMMnet, and some of our professors know about AMMnet. So please, but we want to have a section, a local chapter in Brazil of AMMnet. So we are going to encourage you to put down your name if you are interested in joining AMMnet in Brazil, right? So as we bring this to a close, I want to read out our speech, and we want to thank you, distinguished guests, colleagues, and students and friends. We say good evening to you all, and it is a great honor to stand before you today as we inaugurate the Apply Malaria Modeling Network here in Brazil. This moment marks a significant milestone in our collective efforts to combat malaria through the power of mathematical modeling and innovative research. Malaria remains one of the most formidable public health challenges of our time, despite decades of efforts and considerable progress. It continues to affect millions of lives, particularly in regions like Sub-Saharan Africa, Asia, and even in South America. It continues to be a menace in these continents, especially even in South America. We have in the Amazon area of Brazil. Our work, therefore, is not only important but also urgent. It is within this context that AMMnet was born, a network dedicated to advancing the application of modeling techniques in the fight against malaria. And AMMnet is being sponsored by Bill and Melinda Gates Foundation, and they are the major sponsors of this workshop. And we hope that we can continue to have workshops like this annually. Would you like it?
Yes.
So today, we are not just launching a network, we are building a bridge between disciplines, uniting experts in epidemiology, statistics, data science, public health under a common goal to develop the fundamental and useful techniques of mathematical models that can inform policy, guide interventions, and ultimately save lives. The potential of applied malaria modeling is vast, from predicting outbreaks to optimizing resource allocation, from understanding the impact of climate change on malaria, understanding DNA sequencing, as we have seen this morning, and even understanding the dynamics of transmission, and even more control strategies. Our work here will touch on all these critical areas, but this potential can only be realized through collaboration, innovation, and a shared commitment to excellence. In this light, I want to highlight a few key aspects of our mission at AMMnet. Number one, interdisciplinary collaboration. We have already started that. We are going to start collaborating, doing research together. At the heart of AMMnet is the belief that the best solutions emerge when diverse perspectives come together. We'll foster an environment where mathematicians, statisticians, biologists, and public health experts work side by side, and each bringing their unique insights to the table. Number 2, capacity building. We are committed to developing the next generation of researchers and practitioners in malaria modeling through workshops, training programs, and mentorship opportunities. We will equip professionals and students with skills that they need to make meaningful contributions to this field. Number 3, innovation in modeling. The landscape of malaria transmission is constantly evolving, influenced by factors such as drug resistance, vector behavior, and climate change. AMMnet will prioritize cutting-edge research, leveraging the latest advancements in machine learning, artificial intelligence, and computational modeling to stay ahead of these challenges. Number 4, global collaboration. While AMMnet is rooted in Brazil, our vision is global. We will actively seek partnership with organizations and networks around the world, sharing the knowledge, data, and best practices to amplify our impact. Number 5, policy engagement. Our ultimate goal is to translate complex models into actionable insights that can guide and practice, and that can guide our practice in propounding policies and helping policymakers to also formulate policies. We will work closely with policymakers to ensure that our research informs decision-making at the highest levels, both in Brazil and internationally. As we embark on this journey, let us remember that the stakes are incredibly high. The work we do here will have a direct impact on the health and well-being of countless individuals. It is the responsibility that we must take seriously, and I have no doubt that together we will rise to the challenge. In closing, I want to thank our keynote speaker, Professor Alves. Please, can you come and sit here? She's going to form, together with Professor Veronica, going to form part of the major stakeholders of AMMnet in Brazil. Please come over here. So I want to invite Professor Kristen to also come here. So we hope that with this formidable team, we can do something together that will really propel AMMnet in Brazil further. Now, I want to express my deepest gratitude to this great team, our partners, our collaborators, and supporters. Person of AMMnet in the Northwestern University in the US. Let's give a round of applause to AMMnet. And we also want to thank the director of IMECI, Professor Ricardo Miranda, and his team. He was here with us on the first day. And we want to thank our able representative here at IMECI and our co-organizer here at IMECI, Professor Veronica. And once again, we thank Professor Luciana Alves, the malaria keynote speaker. And we have Professor Christian here from USP. So we are going to start the team here. And we want to thank Professor Paulo Rodriguez from SALI, the director of SALI. He is not here, he's unavoidably absent, but he will have been, he's willing to be here today, but he can't be here at this moment. So we want to appreciate all our LOC members. We want to thank all the members of the department, members of team, organizing committee, all our friends who have come here to support us. We want to really, really thank you. We say thank you to Tope, we thank you, Mike, yes, thank you, Priscilla, Negli, Deborah, is not here, and Ademir, we thank you so much. And to our wonderful students, we really, really thank you. Great students, we can see that we have great researchers and in making, and AMMnet is really contributing to their research skills. So I want to let us know that your dedication and hard work going forward will move this foundation forward. And I believe it will be a transformative force in malaria control. Now let us move forward with this determination, creativity, and an unwavering commitment to excellence. The task before us is great, but so too is our potential to make a lasting difference. So once again, I want to thank all of you who have supported this workshop and who have attended this workshop. I want to say a very big thank you to you. Please, all the things that you have learned here, don't let it go down, don't let it die down. Please continue to apply them and continue to be in touch. And we want to see the results of what you have learned. We want to see the impact. So once again, I want to thank you, and I look forward to the incredible work we will achieve together. Thank you very much. Thank you so much. Thank you. Thank you. Thank you. Thank you. Thank you. So right now, for those of us here, I want to invite Professor Veronica and Professor Luciana to present the certificates. Please, Julia Source, come for your certificate. Some of them have to travel, so some of them are not here. Michael Fabi, come for your certificate. Okay, Nicholas first. Nicholas. You can, okay. Nicholas, you want to have a handshake with Okay, Michael, Priscilla, get ready. Let's give him a round of applause. So we can take one AMMnet slide. Maybe? It's not here. Please take your Priscilla.
Júlia, você tira uma foto aí com ela, tá bom?
Yeah, tira a foto.
Dançar ela tá propaganda. Pois é.
Yeah, this right.
Christian.
Diego da Silva Santos is here. No, Nicolas.
I'm sorry, Anderson. Anderson, okay. Okay, thank you. Anderson. No problem. So thank you, Professor.
Some people need to request the certificate here.
Yeah, okay, let's give Negli this one.
To simulate.
Negli, just to simulate. Negli?
Simulate.
Yes. Random. So let's come for a group photo over here. Thank you, everyone. A round of applause for yourself. So we asked our keynote speaker to say a few words and declare the workshop closed. You can say in Portuguese, and then Veronica will say something. One minute. One minute. Veronica. Okay, Veronica, declare the workshop closed.
Okay, with a picture, with a special picture here. We start with small things. The idea is to grow, to use this moment to start a new moment of research. And thank you very much for all of you to be part of this. Thank you very much for all speakers and all the participants. Thank you very much, and we close this meeting with this act. Thank you.
Okay, so.
Does everybody have the AMMnet sticker? So you just hold it.
E o café parece que espera pela gente.
Okay, por favor.
Another one, he said she just hold it.
Todos pessoal.
And you can borrow.
He said we should go this for another picture.
We're gonna hold it and take a picture.